Okay, here we'll do section 7.3 and do example 2. In this one, they actually give us x as a function of y. They're being very nice to us that way. They tell us that x is equal to e to the negative y squared. Now, I suppose, they could have started with what? That negative y squared was the log of x. And so that would have been y squared was minus the log of x, which is kind of interesting. And then if I'm going to be able to take a square root of something like that, so y equal square root of minus log of x. Now I could also write that with that -1. It wouldn't look so much like a negative. It would be natural log of 1 over x, because I'd bring the negative up and make that x to the -1. But I would have something like this. They could have started with that, but it's important to realize, the log of this thing would have had to been greater than 0, and greater than 0, greater than 0. The log of it would have needed to be greater than 0, and so here greater than or equal to 0, I guess. So here, this tells us that x would have had to been at least 1 oh wait, other way around. It could be no more than 1, right? So 0 could be less than x, less than or equal to 1. And because then, like x equal 1/2, we get the log of 2, which is a positive number. So so we would have that. In this case, they do it all this way, and so that's nice of them. They start that way. They could have given us this, and we would have had to solve for x. And at any rate, we're given that, and so if one looks at that curve, I guess it looks like that. I'll take their word for it. And they would like this area here, all in there, to be rotated around the x-axis in example 2. And so if you're going to do that, that's fine. And again, you could make a disk, but we're not going to, because this example is for the shell method. So in making shells, I'm going to slice this way as I'm rotating around that way. So notice that with the shell method, the slices are parallel to the axis of rotation. Okay, I'll even write that down. Slices parallel to axis of rotation. So remember, with the disk method, they were perpendicular to the axis of rotation. And so we're going to rotate these things around to make our tin cans. Here is the radius, and there is the height. And so the height, right, we get that from our x value here of e to the negative y squared, and our radius is just our given value of y. So r is just y, and they're telling us to go from 0 to 1. And so that is our integral from 0 to 1. I need my tin can here that is 2 pi r by h. And so as I look at this, my 2 pi r, so there's 2 pi. And then r was just y. and then h was e to the negative y squared, and then dy for our thickness. And so we have that integral. I'm going to let u equal negative y squared. Then du is negative 2y dy. And so this becomes 2 pi. Now, this is interesting. Notice that this is u of 0 is 0, and u of 1 is actually negative 1. So that'll be interesting. So we go from 0 to negative 1. Backward limits there, but that's okay for our integral. And we have, and I need to take care of that negative 2. So actually, there's a 2. So I'm going to get rid of that 2, 2y. And I just need a negative out here, right? A negative there and a negative in here, so that I could bring that 2 in here. I have a negative 2y. So I get a negative pi on the outside, 0 to negative 1, e to the u du. So this is negative pi times e to the u from 0 to negative 1. And so this is negative pi times e to the negative 1 minus e to the 0. Well, e to the 0 is 1. And if I take care of the negative here, I end up with pi times, send that negative through, I get a 1, and then minus e to the negative 1. And hopefully that's what they got. Yes, it is. Okay, so so that is our volume in that case using the shell method. Again, I could have just used the disk method with this other function here. Now that might have been pretty ugly trying to get the antiderivative of that. And so that also shows why one method may be preferred to another at any given point in time, because here I'm not sure I would have been able to do the resulting antiderivative, but when I did the inverse and did things, x in terms of y, and went to the shell method, of course they set it up this way, but it worked. That I could do the antiderivative relatively straightforwardly, a little bit of substitution there. And so, it's just either method can find the volume, but one method may be preferred to the other. So let's go ahead and just try this. Now the question is, if y is going between 0 and 1, what is x actually going between? Because I said this function is defined here between 0 and 1. But if y is 0, x is 1, right? So y equals 0 implies x equals 1. And then if y is 1, we get e to the negative 1. And so in our case, we'll do limits between those. And so let's check this out with Desmos. Let's continue this example and check it out with Desmos. So I'm going to try it. Hadn't tried it yet, so we'll see what happens. But again, oops, that didn't connect there. So we want to do this area. Here's 1 over e. Here's 1. This is y equal the square root of the log of 1 over x. Right, that's what I had there, yeah. Now notice from 0 to 1 over e, we had a constant 1. So now if I make my disks this way, then from 0 to 1 over e, I just have my pi r squared there is pi and 1 squared dx. But then from 1 over e to 1, I need my pi from 1 over e to 1. I need this natural log of 1 over x, because I squared it, right? Natural log of 1 over x dx. Now actually, I think about it. So here on this first one, we get pi times x evaluated from 0 to 1 over e plus, now here log 1 over x, remember that's just negative log x. Oh, okay. So I could look up that antiderivative. Again, we don't know that antiderivative unless we look it up. Now I can move the negative out, so I can do minus pi here. Now that antiderivative of that thing, let's get rid of the minus. I think might be x minus x, x log x. That might be it. Take the derivative of this, right? I get 1, and then minus log of x, and then minus x over x, which is 1. And, oh, well, that's interesting. That is a minus log of x. How about that? When I take the derivative of this, that's cancels and I get minus log of x. And so actually I want to leave that as a plus, make that a minus log of x. And so my antiderivative here is x minus x log x. So we don't know how to do that antiderivative, but we could look it up. And that goes from 1 over e to 1. So placing everything in there, I get a pi times 1 over e, or pi over e, plus pi times 1 minus 1 times log of 1. Okay, well, that part is 0. So I get that, and then minus 1 over e minus 1 over e log of 1 over e. Okay. So this pi times 1 over e, here's a pi times minus 1 over e. So that's going to disappear along with that. And so I get a pi times 1. And now log of 1 over e, that's just the negative of log of e. And so this thing becomes a positive 1 over e. And there's a minus still. So we get minus 1 over e. And so there was the disk method, and it gave us the same answer as the shell method. Okay, so that's an elongated version of example 2.